Hello, 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 ladies and gentlemen. We're going to start looking at the Hypatia series of contests, beginning with the 2003, which is what we're going to cover in this video, and then we'll cover question 2 in the next video, 3 and 4. So the first 4 videos will be about 2003, and then we'll continue on. So if you're unfamiliar with the Hypatia contest, it is the grade 11 contest, math contest, put out by the University of Waterloo. And it's not to be confused with the Fermat contest, which is also aimed at the 11th grade level of math. But the Hypatia requires written solutions, whereas the Fermat is just multiple choice. You bubble in if you know the answer. And so on the Fermat, it's very easy to take a guess. On the Hypatia, you really need to know what you're talking about. You need to write full solutions. You need to justify everything. So in that sense, it's a little bit of a harder contest. It's definitely the harder of the three. The Freie, the Galois, and the Hypatia. These 3 contests are the written contests. And they're good preparation for the Euclid contest put out by the University of Waterloo, which, if you're interested in attending Waterloo, is a great way to get scholarships for math. Okay. So if you have never seen this, the Hypatia before, or this particular Hypatia, the 2003, feel free to click the link in the description down below, and it will take you to the CEMC contest website. You can see this contest. You can find their solutions. You can look at other contests in the Hypatia series. Or, if it turns out that this Hypatia is too hard for you, feel free to go back and try the Galois and the Freie. So that's the 9th, Galois is 10th grade level, and Freie is 9th grade. And so if you're unfamiliar with writing out solutions and justifying things, the easier contests might ease you into that a little better. Right? If you're in grade 11, practice the easier ones, but ultimately if you're going to try and write a contest, you have to write the Hypatia. If you're below grade 11, then absolutely welcome, and you're certainly welcome to write the Hypatia, although you might be better suited and might get a higher score on the Galois and the Freies. But that's enough about the Hypatia. Wonderful little introduction, if I do say so myself, but it doesn't get us to the actual math. So how about we take a look at the first question? Actually, let's take a look at the contest in general. Now, the 2003 was the very first year of the Hypatia, so the format is not exactly what you expect if you look at some of the other contests. They don't have their familiar title page. They just have a 2003 Hypatia slapped up there on the top. And particularly in 2003, it's got a slightly different format. There are 4 questions, which we're familiar with, if you've ever seen any of the contests. But they also have these extensions, which are much harder versions of the problem. These have since been sort of eliminated. They don't list extensions to problems, but they do make the problems a little longer now. So nowadays, on question 4 on the Hypatia, you'll probably have an A, B, C, and D. Whereas, they only had an A, B, and C here. I mean, there weren't even any parts to question 3 in this year's Hypatia. So, in that sense, the extensions didn't go away. They just kind of got absorbed into the actual questions themselves. So, as I already hinted at, this video we're going to be doing question 1. The next video we'll do question 2, and 3, and then 4. I'm not going to do the extensions because it's not a regular part of the contest as we know it today. 2003 was the only year they had extensions to problems. That said, if there's enough fan demand, maybe I'll go back and look at them. But for now, let's get to the actual contest. So, question 1A. Quinton has a number of square tiles, each measuring 1 centimeter by 1 centimeter. He tries to put these small square tiles together to form a larger square that has side length n centimeters. But he finds that he has 92 tiles left over. If he had increased the side length of the larger square to n plus 2 centimeters, he would have been 100 tiles short. So he had too many tiles for an n by n square, but he has too few tiles for an n plus 2 by n plus 2 square. So he would have been 100 tiles short of completing the larger square. How many tiles does he have? Okay. So what we're going to get is we're going to be able to figure out the total number of smaller squares he would use in each of the 2 larger squares he tries to construct. We know how few or how many he has left over, so how many he's missing or how many he has as a surplus. And using those together, we can try and find some sort of equation or formula for n. Now, if you're experienced with these things, knowing that you're going to be dealing with squares, you're probably going to do n squared and n plus 2 squared, and you're going to be left with a quadratic formula most likely. But even if you're not, you can try and put these sorts of things together. You can say, oh, small square tiles, and it needs to have side length n centimeters. So that means on each side he's going to have n of the small square tiles. So how many square tiles does he have overall? He has n squared. So let's let T be the total number of tiles. Now, our first statement says that if he tries to create a rectangle or a square with side length n by n, then he has 92 tiles left over. So that means that T is, well, how many squares in an n by n square? Or, yeah, how many of the small squares in the n by n large square? N squared. And then he also has 92 left over. Now, the second statement is a little trickier to parse, but basically it says if he were to make an n plus 2 squared, a square of side length n plus 2, he would need to have n plus 2 squared number of tiles. But he doesn't have that. He is exactly 100 short. So we subtract off 100. So T plus 100 is going to be equal to n plus 2 squared. So we get these two sorts of statements here. Now, by themselves, they can't actually figure out the total number of tiles, which is exactly what we're asked for. How many tiles does Quentin have? But we can equate them. And expand them out and solve for n. And once we know n, we can plug it in here, n squared plus 92, and we'll know exactly the total number of tiles Quentin has, and that's what we're asked to figure out. Never ever forget the goal of what you're trying to figure out. Okay. So I don't like this n plus 2 squared in here. I want to expand it out. So you can use FOIL, so firsts, lasts, outsides, insides. And you'll get n squared plus 4n plus 4 minus 100. N squared plus 4n. 4 minus 100, you can grab your calculator out for that if you need to, but it's minus 96. Okay. So we have n squared plus 92, same as n squared plus 4n minus 96. Okay. Well, let's get everything over to one side. We'll get a single equation. It'll all sort of equate to be 0. So we can say 0 is n squared plus 4n minus 96, and then we bring over this n squared, and we bring over this 92. So our two n squareds are going to cancel each other out. And this 96 and this 92, they group together to become minus 188, I believe, but let's just double check that with calculator. Yep, 188. And of course this 4n, he doesn't really combine with anything. So we're just left with 4n by himself. Okay. Well, if we bring the minus 88 over to the other side, we get 188 is equal to 4n. And if we were to divide both sides by 4, we would get n is equal to 47. Okay? Now don't stop there, because we're not asked to figure out n. We're asked what is the total number of tiles Quentin has. And n is just a little piece of the puzzle. Now we need to figure out t. N squared plus 92. So that's 47 squared plus 92. 47, sadly that's one of the squares that I don't know off the top of my head. But it's 2209 according to my calculator. And so when we add on 92, we get 2301. And so this should be our final answer. 2301 is the total number of tiles Quentin has. Now, if we wanted to, and by all means, you don't have to do this, but if you want to, if you've got time, you know, you're doing the contest, you're finished, you want to go back and check things, or maybe, you know, it's your first time writing this, and, you know, you're not really sure of 3 and 4, so you're not even going to bother attempting them. You can go back and double check, hey, does this final answer of t equals 2301, does it satisfy all the criteria? Okay, so we've definitely figured out n is 47. We could double check, does n satisfy the equations we're talking about? Does the t we have satisfy the equations we're talking about? And that's a good way to check that your arithmetic and that everything you punched in on your calculator all worked out. Okay, but you don't have to. If you're confident in your answer, by all means, stick with that. But if we wanted to, we could double check, hey, 2301, 47 plus 1, or plus 2 squared minus 100. Well, that's 49 squared minus 100. And 49 squared is one of the ones I do know. It's 2401. So we were able to check it, and it does indeed work. So obviously t satisfies the first equation. That's how we figured out what t was. But we double-checked that, hey, the t we computed definitely also satisfies the second equation with the same value of n. So 2301 is the number of tiles Quentin has, and if you want to, you can leave sort of a therefore statement to that effect. All right, now on to B part for this question. Quentin's friend Rufus arrives with a big pile of identical blocks, each in the shape of a cube. Okay. Quentin takes some of the blocks, and Rufus takes the rest. Quentin uses his blocks to try and make a large cube with 8 blocks along each edge, so it's going to be an 8 by 8 by 8 large cube. But he finds he's 24 blocks short. Okay, so we can actually figure out how many blocks Quentin has, and maybe that'll come in handy. It'll be 8 times 8 times 8, the total number of blocks he wishes he had, minus 24. He's 24 blocks short. Rufus, on the other hand, manages to exactly make a large cube using all of his blocks. Okay. If they use all their blocks together, they are able to make a complete cube, which has a side length that is 2 blocks longer than Rufus's cube. How many blocks are there in total? Okay. So we have a couple things we want to figure out. As I remarked, Quentin, we can probably figure out the number of blocks he has. It's going to be 8 times 8 times 8 minus 24. And Rufus, well, we don't know how many blocks he has, but we know we can form a large cube. So let's say that that cube has side length r. Okay. We grab ourselves a brand new sheet of paper, of course. Eight cubed is the same as 8 times 8 times 8. There are 3 8s, so it becomes 8 cubed. Minus 24. And 8 cubed is 512, so minus 24. And we get, I think, 488. Okay, and we'll just double check that with calculator. Yeah. So we know how many blocks Quentin has. That's not the major difficulty here. We want to know how many blocks there are in total. Well, hey, if they use all their blocks together, then they can create a cube. So right from there, we know the total number of blocks is definitely going to be a cube. And it's related in some way to the size of Rufus's cube. So hopefully, just like the first question for part A, we're able to come up with some sort of equation here. So we'll label two things. We'll let r be the side length of Rufus's cube. And just as before, we'll let capital T be the total number of blocks. Okay? Well, we know that the total number of blocks forms a cube that has a side length 2 greater than r. But we also know that this is how many blocks Rufus has, which forms a cube, so it's r cubed, plus how many blocks Quentin has, which is 488. Okay? And now, hopefully, we can expand this out. So r plus 2 cubed equals r cubed plus 48. And now we can either use the binomial theorem, or the binomial expansion here, or we could use repeated sort of FOILs. But I know it's going to be r cubed plus 3 times 2 to the 1 r squared plus 3 2 squared r to the 1 plus 3 2 cubed and r to the 0 equals r cubed plus 488. We can simplify this. R cubed plus 6r squared plus 12r plus 24 is equal to r cubed plus 488. Okay. So we can do things. We notice there's an r cubed on both sides, so those guys will definitely cancel out. And we'll be left with 6r squared plus 12r plus 24 minus 48 is equal to 0. We're moving towards a quadratic formula. We have r squareds, we have r's, we don't have r cubes or anything else. And 24 minus 488. Okay, so that's 6r squared plus 12r minus 464. And that's equal to 0. Okay. Now, it'd be really nice if I could divide by 6, because certainly the r squared and the 12r have a factor of 6. But 464, unfortunately, doesn't divide by 6. It does, however, divide by 2. So I could divide everything by 2, and I'd say 3r squared plus 6r minus 232 equals 0. And I do this just because I'm about to apply the quadratic formula. I want to make my life a little easier. So we're going to get two possible values for r, negative b plus or minus. That's where the two values come in. Now, one of them is going to be negative, and you can't have a negative number of side length for a block. So that's how we're going to tell whether or not that one is true, or that's the desired r. So negative b plus or minus the square root of b squared minus 4a, and c is negative 232. Okay, can't forget the minus sign there. So it's negative 6 plus or minus the square root of 36 plus, these two minus signs make a plus, 12 times 232. That's 2784 all over 2. Okay? So we continue on with our calculation. R is equal to negative 6 plus or minus square root of, so 2,784 plus 36, 2820, and hopefully that's a square. It isn't. So have I done something wrong? right? Because R should be an actual number of blocks. It should be a whole number. So somewhere in here, I think I have messed up a calculation. Divided by 2 here, I got a 6, I got a 3. 464 definitely divides by 2 to become 232. Multiply that by 12, I get 2784. If I add on 36. Okay. So the fact that this number in here is not a perfect square means that R will not be a whole number. And R definitely needs to be a whole number, so that means that I've misread something. Quentin uses all his blocks, makes a large cube with 8 blocks along each edge, but he finds these 24 blocks short. So you should be 8 cubed minus 24. So I have no doubt that Quentin does in fact have 488 blocks. And Rufus creates a large cube, so he's definitely R cubed. And the side length, using all their blocks together, so R cubed plus the 488 of Quentin needs to be R plus 2 cubed. Okay. So I agree that this first page here is correct. Now, did I expand this properly? R cubed. Ah, there it is. There shouldn't be a 3 here. It should just be 2 cubed. Okay, so thinking critically about the numbers that you're using definitely helps. So if I had just blindly performed that calculation, we'd have some weird number R of blocks, and it wouldn't be a whole number, and that makes no sense. So R squared plus 12R plus 8 equals R cubed plus 488. So once again, the R cubeds cancel out, and we're left with 6R squared plus 12R plus 8 minus 488 equals 0. Well, that's 6R squared plus 12R minus 480 equals 0. Well, finally, these guys all do divide by 6. So R squared plus 2R minus 80 is equal to 0. And now let's see how the quadratic formula fares. Negative b plus or minus the square root of b squared minus 4a, which is just 1c, all over 2a. Oh, and come to think of it, I think I was performing the quadratic equation wrong the last time. I should have had 2 times 3 on the bottom, not just 2. Okay. So we can work with this a little better. Plus or minus. Once again, one of the R values is going to end up being negative. The negative 2 minus something will be negative, and we'll know we don't need to count that one because you can't have a negative side length for blocks. So 4 plus negative 4 times negative 80. So 320, and that's going to be 324, which is definitely a square. It's 18 squared, I believe. 324 divided by 2, negative 2 plus or minus 18, all over 2. So that's going to be, everything on the top has a factor of 2, so we can cancel it out. We're left with 1 and 9. So -1 plus or minus 9. So r is going to be 8 or -10. Can't have a negative side length of blocks, so r is going to be 8. So Quentin tries to make an 8 by 8 by 8 block. Rufus actually succeeds in making an 8 by 8 block. And we're asked for the total number of blocks again. Well, total number of blocks was r plus 2 cubed, because all the blocks together made a cube. And that'll be 8 plus 2 cubed, so we sub in the r value we need. Since it's a written question, I guess we should probably explain why not -10. Can't have negative side length. Okay. So 8 plus 2 is 10, so 10 cubed, so we're going to have 1,000 as the total number of blocks. And what we can do is double check. I was talking about this with part A. We know the number of blocks Quentin has is 488. And now we know Rufus tries to make an 8 by 8 by 8 cube. So that has 512 blocks, and if we add those together, we do get 1,000, which is 8 plus 2 equals 10 cubed. So all the conditions of the question are indeed satisfied by our final answer, and now we know how many blocks there are in total. So it was a good question. I liked it. I thought there was going to have to be some quadratic formula shenanigans in part A, but it turns out no. But we did have some quadratic formula stuff in part B. And I do apologize with my expansion of r plus 2 cubed. I'll try and do better in the future, but, everyone's liable to make mistakes. You need to understand how you can recognize when you make your mistakes and what you can do to sort of track down where your mistake is. So, not a total loss there. And that's question 1. So feel free to join me as we continue on with the 2003 Hypatia, and we'll look at question number 2 in the next video. Thanks for watching.